Hello, my name is Zachary Chenoweth, and this is my presentation for Lab 3, Task 1, Motion Estimation. Now, for this task, all we have to do is get the robot to navigate all the cells inside this grid. And then we have to use motion estimation to estimate the coordinates and orientation of the robot. In this task, the robot will always start in cell 16 facing north. And the cells are numbered 1 through 16, starting from the upper left corner down to the bottom right corner, going left to right. Starting off, we have all of our basic initializations for the robot, for the position sensors, the IMU, etc. I have a array to hold the basic units for the grid, so that way we can see which cells we have visited and which ones we haven't. The cells that we have visited is going to be labeled as an X, and the cells we haven't visited are going to be stars. This array holds the X and Y coordinates of the middle of the grids of each of these cells. So we can see the general coordinates. We have some variables that we will use later down the line for initialization purposes. Our first function is for our forward motion. This uses the position sensors to move about 10 inches forward. For this part, we're using the non-noise. This is the non-noise task, so we don't have to worry about noise to the position sensor at all. All we're doing is taking the value that the position sensor reads and subtracting the starting position that we read earlier. And then while we are moving forward, as soon as it hits 10 or greater, then it's going to stop the robot, and then it's going to deliver the total distance traveled. This function is my turn function, and basically we are using the IMU to turn 90 degrees to the left. For this task, I decided to only make left turns just because I found that it was the easiest. So we're going to read the angle, and if the angles are facing north, south, east, or west, it goes into its designated if statement and performs the turning motion. The current position calculates the X and Y coordinates, and it does that just by adding the distance traveled and incrementing the previous position, adding and subtracting based off of which cell it moved to. So if it's going north, it's going to add the distance traveled to the y-axis. If it's going south, it's going to subtract. If it's going east, it's going to add to the x, and if it's going west, it's going to subtract from the x. This function updated grid updates that grid block that I showed you earlier to put an x where the cells that we have visited are, and then it also prints that grid and then returns the index +1, so that way we know which cell that we are in. This function just prints all the information at the end, so we get the X and Y coordinate, the current cell, and then the current angle. Cells visited will check and see which cell we are currently in, so we can account for it appropriately. And it returns true or false depending on if we have visited that cell already. So later down the line, when the robot is making its rounds, if it sees that it has visited that cell previously, it'll make it turn. And then this check done function basically just checks if we have visited all the cells in the grid. Here's our main loop. So first thing we do is we're going to calculate the current position. We keep track of the previous position, so that way it can be used in this function later. We get the current cell number, and the current angle, and then we print the information. Then we're going to check if we visit all the cells, and then we're going to move appropriately. So if the robot is in one of the corners, so in cells 4, 1, 13, and 16, if it's in one of those corners facing the wall, then it's going to make the robot turn, otherwise it'll travel forward. All right, so now that's the code, so let's go ahead and see it run. So you can see as it moves forward, it's going to print that its current position as well as the grid. And you can see as it hits the new cell, it's going to update the grid as it's moving along. And we can see that the X and Y coordinates are properly calculated. So we can see that in each cell, it is about where it's supposed to be with some slight error. And this is to be expected because the position sensor doesn't stop at exactly 10 every time. Sometimes it'll be more, a little slightly more, and sometimes it'll be slightly less. But because the position sensor is pretty accurate, we're going to get fairly accurate units. Now, when I was making the robot and deciding what speed I wanted to set the robot to, I decided to make the forward motion about pi, so 3.14 radians per second. And then I decided to make the turning motion about 0.5 radians per second. And I did this because in the past I have had some issues where if you move too fast, the IMU won't catch the values as accurately. So I wanted to make sure that I prevented any sort of mistake or hiccup in that. And then once it's visited all the cells, then the robot stops and the program ends. That's the non-noise solution. Let's go ahead and take a look at the noise solution. Now this is basically very similar to the previous one with some slight adjustments because we have noise to the sensors now. Again, we have all of our initializations, the grid, the cells, and then you can see we have two new variables here. Again, we'll be using those later. This calc velocity calculates the velocity we want to turn, because instead of using the IMU like we did for the non-noise solution, I decided to go with an easier route of doing a 90-degree turn based on time, because I know that noise will not affect that turn because I'm using kinematics to calculate that 90-degree turn, and it's going to be pretty close. Again, it might be slightly off by a few decimal points, but not enough to be super significant. Again, we have our forward motion. This is basically the exact same thing as the other one. The reason I haven't changed this at all is because when I was trying to prevent the position sensor solution, I noticed that with this function as is now, the noise in the position sensor isn't enough to drastically change its values, so I still get about the same as I did for the non-noise solution. So I decided not to change anything and just leave it as is because the noise doesn't affect this. So that is why this is the same. And then as you can see, our turn function is different because I am stopping it based on time. So I decided to make it turn 90 degrees in 1 second using that function that I showed earlier. And so while the time is less than 1 second, it's going to keep turning, and then it's going to stop. And then we have to adjust its orientation. So I use north, south, east, and west just for ease. And then I'm going to return that orientation so I can adjust the actual angle later. This function is the one that's going to actually change the angle. So it's going to read the orientation that I passed back from this. And it's going to say if it's north, then the angle is 180. If it's south, it's 0. If it's east, then it's 90. And if it's west, it's -90. Just because I know for a fact that I'm turning 90 degrees almost exactly every single time. So I'm just going to approximate and say that I'm about at these angles. Again, the true angle might be off slightly, but when I was doing the solution, I found that the IMU readings were all over the place, and instead of doing a bunch of averages and stuff that might not be correct, I decided to take what I thought was the easier route and just say not use the sensor, because we are not required to use the IMU if we do not want to. The current position is slightly changed as well because now we're using based on that orientation letter that I was showing earlier. But the addition and subtraction is the same. So if it's facing north, it's going to add to the y. If it's south, it's going to subtract. East will add to the x, and west will subtract from the x. Print information is the same. It's just going to print all the information out, the x, y, the orientation, and the cell number. Update grid is also exactly the same. It's going to update that grid that we showed earlier. Check visited, again, is going to check if we've visited the next cell that its robot is thinking about going to, and return 1 or 0, respectively. Check done is just going to check and see when we visited all the cells, or if we have visited all the cells. And then in our main loop, we have the same setup as we did before with the new functions in mind. So now let's go ahead and see this one run. And as you can see, the x and y coordinates are pretty much similar, if not exactly the same as the non-noise solution. Again, that's because of the position sensor noise not really affecting its reading because of how I have my code. So you can see as the robot travels, it's updating the grid. We're getting the new cell numbers every time, and then you can see the angles changing as it's running through. So we'll speed that up, and you can see it circles around, and you can see we get all the updates and stuff, and then as soon as it's done exploring, then it's going to end and stop. So that was my presentation for Lab 3 Task 1 with and without noise. Once again, my name is Zachary Chenoweth, and I hope you have a wonderful day.